Okay, so all right, so let's figure out how we invert the exponential, because this allows us to, given a point, write out what its polar coordinates are in particular. Right? So this will give rise to defining the logarithm, and here we'll start seeing issues with branches and functions that may be defined in more than one way and things like this, which actually in the forum there was already some discussion about, right? When talking about the square root, we already saw an example of this. Okay, so let's see. Okay, and then the plan is to, so the roadmap is basically we finished this sort of calculus in the or algebra of complex numbers now. And then one thing that there was asked in the forum too, which was with regards to, I haven't been very precise in when I mean the function is differentiable, if I mean that it's just differentiable at a point, or differentiable in the neighborhood of a point, or differentiable everywhere. Right, and so we'll revise just basic point set topology to be able to talk about neighborhoods, open sets, complete sets, and compact sets, and so on and so forth. And this will allow us to better talk about, to be much more precise about where we want the functions to be defined, where we want them to be differentiable, and so on and so forth. So that's the plan. Right, so for now, we've talked about differentiability at a point, right? Of course, the function needed to be defined around the point because we needed to take this limit of things around the point, but we didn't talk very much about whether the function should be differentiable at the point and the points nearby and things like this. We haven't gotten there much, except when we talked about power series and the radius of convergence, right? But sort of modulo that, we haven't addressed this very much yet, and so we'll introduce some point set topology to talk about this. And then after we're done with that, we'll go into integration and prove Cauchy's theorem and start exploiting Cauchy's theorem to give us many properties of analytic functions. Okay, so just a bit more of algebra, right? So periodicity. Right, so we say that a function fz has a period C if f of z plus c is equal to f of z for all z. Okay, so if we have a function, right, this is the sine is periodic and the cosine is periodic and so on, right? And in particular, right, we know that the sine has period 2 pi and the cosine as well. Right, for all x, and in particular, this holds for all for all complex numbers too. Cosine of cosine of x, right? So sine and cosine have period have period 2 pi. Right, the angle, right, going around the circle a full time. Right, 2 pi is just corresponds to going around the circle full time, and then everything looks the same. Right, and it's a good exercise to just, try to do this with x being a complex number and show that this is still a period. Okay, so in particular, we immediately get that e to the I 2 pi, for example, right? What is this equal to? By Euler's formula, this is just cosine of 2 pi plus I sine of 2 pi, right? So this is equal to just 1. Okay, so in particular, it means that e to the z plus I 2 pi, right? This is equal to, okay, I can do this way, right, is equal to e to the z times e to the I 2 pi, right? But this is just equal to 1, and so this is equal to e to the z. Right, so in particular, it means that e to the iz, I mean, we can view this in two different ways, right? Either the exponential is period I 2 pi, or the exponential with an I already inside as period 2 pi, right? It says period. Okay, and it's exactly, right, because corresponds with going around the loop. Okay. Okay, so now let's talk about the logarithm. Right? The logarithm is simply, right, if I have that w is equal to e to the z, then I want to define z as the logarithm of w, right? That's how we define the logarithm also over the reals, right? So few things become immediately obvious, right? Which is w cannot be 0, so we can only define the logarithm of things that are non-zero. If something is 0, then there's no way we can define the logarithm for sure, right? And now, let's say that we want to compute the, right? Let's say that we want to calculate the logarithm. So let's put things in terms of real and imaginary parts, right? So let's say we have something like this, right? And now x plus y, right? So just write the same thing again. Right, x plus iy is just equal to the logarithm of w. Right, so what do we know about this? We know that, right, x and y are real here, remember. So e to the x should be equal to the absolute value of w, right? Because we know that, this will be e to the x times e to the iy. E to the ii is norm 1, so e to the x will be the absolute value of w. Right, so this means that, the log x, the value of x, is just equal to the log of the absolute value of w, right? This is like the log over the reals, right? Just the real logarithm, right? The one that we're used to. But now we have to understand what happens with y, right? So what we know is e to the iy is equal to w over the norm of w, right? And so in particular, right, there's a few things. So y is defined up to multiples of 2 pi I, right? Of 2 pi, right? Because if y is a solution to this, then, y plus 2 pi is also a solution to this, right? But we know that this is equal to cosine of y plus I sine of y. Right? So this means that we want cosine of y plus I sine of y to be just w over the absolute value of w. So effectively, y is just the angle, right? What we call the argument of w, plus, of course, k times 2 pi for any k an integer, right? We can always pick any of these, right? Where the argument is just, another way to call this would be the angle of w. Okay, so let's make this a bit more clear. Okay, so this means in particular that, right, so let me write this way. So, right, so if I have something like e to the I y equals w over w prime, right, so effectively y is equal to what we call the argument of w, right, up to multiples of 2 pi. right? And this will give rise to issues. The fact that this is defined up to multiples of 2 pi, right? But in particular, now we can write, right? We can write the log of w, right? Because now the log of w is equal to what? Well, the real part of the log of w, which is, okay, let me write first like x plus iy, right? But what is this equal to? Well, x is just the log of the real numbers, right? So the real log, right, over the reals, plus I, right? And now here we have what's called the argument, right? And so the logarithm of a complex number, the real part is just the logarithm of the modulus of the complex number, and then the imaginary part tells us the angle, right? And so this one, the issue is that this one is defined, right? I can add or subtract multiples of 2 pi as long as k is an integer, right? And it's still a valid logarithm, right? And so, and I mean, of course, okay, let me write before I go into a discussion of the problems that this might give, let me just say that now if you want to do any kind of like a to the b, right, you can now take just this to be exponential of b log a, right? And you find log a this way, and then you can define any powers of complex numbers this way, right? But in general, it will give rise to problems potentially, right? Because the logarithm will be defined up to a certain multiple, okay? But what's important the thing that's important to take from here is that if I have a complex number, then basically I can write it as radius times e to the I theta, that this is its angle, right? Or that the number is equal to its absolute value times e to the I to this argument, right? And this is really what you should take away from all of this, is that the exponential allows us to write numbers with respect to its modulus and its angle, right? And sort of separates things in that way. Okay, and that's what's going to be crucial. Now, the fact that the logarithm is defined up to multiples, right, is going to give rise to issues, because if you want to define the logarithm, right, there's many possible definitions, what's called branches, and you sort of have to pick one to make a function, right? And so the question is, how do you pick one, right? So what would be natural, of course, is to just imagine that the argument, right, is always, say, between 2 pi and 0, right? This would be the most elegant solution, right? Because, I mean, we rarely talk about angles like 3 pi, right? Usually when we think about angles, we always think of the angles between 0 and 2 pi, right? But now what's the problem with this? The problem is, let's say that I'm taking the logarithm of a number, right? Let's say that I take the complex plane, and now I'm looking at logarithms of numbers, right? Like I'm defining the logarithm. And I define the logarithm, right? I'm here, let's say that I'm here, right? The logarithm is whatever this angle is, right? Let's say that I'm in the complex plane, but I don't even need to be I need to be in the complex plane. Of course, I don't need to be in the unit circle, right? But let's say that I'm somewhere here, right? And I have an angle, I take the log and I get log of the size, right? And then I get this angle. And then I move around in a line, right? And I would like the logarithm to, I mean, if it's supposed to be a nice function, it should, of course, right? It should, of course, stay continuous, right? Move continuously as I move in the complex plane, right? And so I go and I travel around, and the angles I go up, and now they are whatever they are, right? A bit bigger, right? And now I can keep traveling, and I go, maybe I loop around, I do, right? And as I go, this, right, the radius, the distance to the center, for sure changes continuously, and so does the angle, okay? But if I define the angle as always being between these two things, when I go up here, right, I have the angle needs to jump from 2 pi, right, to 0, right? And so this creates some kind of discontinuity, right? And this clearly, I mean, this feels at least like it might bring trouble, right? You could say, okay, so fine, that's fine. We don't need to make the discontinuity show up here. We can make it show up, right? We can just make it show up here. We can say I take all the angles to be between, whatever this is, theta and theta plus 2 pi. But then what happens if I cross that, right? And what happens if I go around more than what I started? If I loop around an entire time, right? The angle that I see here and the angle that I see here need to be the same, right? Because it's the same, right? I can take a curve and go to the same place, right? And so the log should be the same. However, it kept increasing, the angle kept increasing all the way, and it'll be the same, right? So we'll have to have this crash, right? And this discontinuity. And in fact, this is going to give rise to to many issues, but also sort of many opportunities, because this will mean that if I'm integrating, like if I'm looking at things like the log, right? And since the log is the primitive of 1 over z, right? The logarithm is the primitive of just the inverse function. It will mean that if I go and integrate the inverse function around, the integral should look something like log. And if it has a jump of some type, maybe I can see it. And in fact, Cauchy's integral formula will give rise exactly to this. Will allow you to count how many things a curve loops around, and is exactly because it's sort of in a way counting how many times you had to make one of these jumps in the log. Okay, so we'll see all this much later, but just to give you some foresight and some a little bit of a teaser of what's to come, and just to give some intuition. But it should be clear that one needs to be careful now when defining the log, right? When we take the log of number, we usually think about it in this way. But if we want to study how it evolves along a curve and so on, it's clear that we're going to have issues. Right? Oh, I just saw that there were more messages in the chat that wasn't open. Oh, sorry. Let's see. Oh, it was nothing for me to answer. Okay. All right. So. Okay, and I mean this construct of a Riemann surface, which you might see later, is a way to handle this. Okay, let me just leave it at this, and maybe we'll see a bit more about it later. Okay. Okay, so let's talk a little about point set topology now. Let me erase. But in terms of like doing, calculus, not in the sense of derivatives, but calculus in the sense of doing like algebra of complex numbers, this is basically it, right? These are the important properties and functions and so on. And now we can move on to really study, right? To really studying smoothness properties of functions. And for this, we need topology, right? Because we need to know. Right, we need to know what if we want to talk about being differentiable right, we need to know the notion of arbitrarily close to something, right? So if we want to study, smoothness at a point, we need to be able to say what the function's value is. Right, there's basically two things we need to do. If we want to study a function at a point, can we study its smoothness properties or what it looks like locally, right? We need to be able to zoom in and find a set that contains that point, and sort of everything that's like if we were to draw a little ball around the point, that everything is still inside that set. Right, and so we're going to be able to study a function locally at a point. We're going to be able to zoom in enough to see a ball inside the set that's still in that point, right? And so we're going to have to talk about when that's the case and when it's not. And another thing we will have to do is when we have a sequence that converges somewhere, we want it to have a limit. We want it to converge inside the set, which is the notion of closed set. Okay, so let me give some definitions of just basic point set topology, and then I'll just give you a couple of proofs in point set topology, just for you to see the flavor of it, but I'm sure you'll see this. You've seen in some courses, and you probably see again in some other ones. Okay, so you can do topology in a lot of generality. I won't do it here. You'll probably see this in a topology course. I'll just do it in the framework of a metric space. Okay, so what's a metric space?